Welcome to Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Here in the United States, it is the Thanksgiving holiday weekend. While I'm recording in Southern Illinois, Allie, our producer, is working on her other podcast, Big Impact Astronomy. While I'm sure both our families would rather we took the time to relax, neither of us is really wired that way, which is good because we have a lot going on. The second week of December is the American Geophysical Union meeting in D.C. I'll be there presenting with a few thousand other scientists, including fellow Twitch streamer Volcano Doc, Melissa Scruggs. In fact, Melissa and I, along with geology streamer Rocket Sage, are working on a study of how people use Twitch to learn. If you like to learn from streamers, please check out our survey at tinyurl.com/twitchsci. And this is just the beginning of conference season. January will bring the American Astronomical Society meeting, which I am not attending this year, as well as PodFest in Orlando, which I am attending. I'm also hoping that, launch windows willing, I'll be able to catch the launch of Firefly Aerospace's Blue Ghost lander. And if I'm really lucky, I'll get to see Blue Origin. If you are in the Orlando area or on the Space Coast in general and you want to meet up, drop me a message on LinkedIn or Blue Sky. Yes, folks, I said Blue Sky. CosmoQuest and all our team members are over on Blue Sky. While we maintain a presence on Twitter because everyone deserves a chance to learn and, well, let's face it, no one else is allowed to claim our usernames, our random chatter has moved over to the brighter place. If you want to follow along with our adventures in podcasting, conference travel, and consuming way too much sci-fi, we're logged in as Starstrider, Inane English, and Kerbal01. Oh, and pets. You'll also get content about pets. For now, though, it's time for science. This week, we're going to play Whack a Story with a whole bunch of random news before trying to understand how black holes just might be a source of dark energy. All this and more is coming to you right here, right now, on EVSN, a product of CosmoQuest X, and supported through our Patreon. Solar system formation is messy. It all starts with a giant blob of gas and dust, and with that kind of an origin, it's really hard for it to be anything other than messy. And for astronomers here on Earth trying to study solar system formation, half a galaxy away, all that mess can make it really hard to see what's going on. But sometimes we get lucky. Enter future star IRAS 04125+2902. This 3 million year old 0.7 solar mass object is still in the process of starting up all its nuclear reactions. Classified as a pre-main sequence T Tauri star, it has a planet-forming disk that is almost face-on in the sky, allowing us a clear view down onto the star. And it also has a transiting planet that crosses in front of that star every 8.83 days. Oh, and it also has a companion star in a wide orbit, but that isn't unusual. This is the youngest star ever found to have a planet, and it is thanks to that super weird misalignment of disk and planetary orbit that this discovery was possible. Why things are out of alignment is unknown, and because this is the first system this young so far discovered, we don't even know if systems being this out of alignment are normal. This system was found by the TESS spacecraft while observing in the direction of the Taurus-Arisia star-forming region, and follow-up observations and analysis have taken advantage of Gaia, Las Cumbres Observatory, and the Sloan Digital Sky Survey. This work is described in a new paper in the journal Nature, led by Madison G. Barber. According to Barber, quote, "Astronomy helps us explore our place in the universe, where we came from, and where we might be going. Discovering planets like this one allows us to look back in time, catching a glimpse of planetary formation as it happens." End quote. We don't know for certain how long it takes planets to form. Some estimates are as short as a few 100,000 years for gas giants, but in order to start to confine those theories, we're going to need to find, or fail to find, more systems like this one through continued systematic observations. Star clusters in general, and binary star systems in particular, offer us some amazing laboratories for understanding solar system formation and evolution. All the stars in a given cluster will form around the same time and with the same stuff. This means any star-to-star variations we see are most likely due to mass variations. In the situation of binary stars, this can get weird. More massive stars form faster and burn through their fuel substantially faster than small stars. When two stars of very different masses end up orbiting each other, it's possible to find a stellar remnant chasing a main sequence star around the sky. While it may look like a young star and an ancient star, they are actually the same age, but the white dwarf started as a massive star and effectively died young. These kinds of systems can go through all sorts of weird evolution. In some cases, the smaller star will consume the white dwarf in its atmosphere when it evolves into a red giant. Sometimes the white dwarf will gravitationally strip the atmosphere off its companion until one day it explodes as a supernova. To understand all the ways these systems can evolve, we need to first understand all the ways they can form. Toward this end, researchers led by Stefanie Gordin have put together the first ever catalog of candidate white dwarf main sequence binaries in open star clusters. Consisting of 52 candidates in 38 clusters, Grandin says, quote, "This observational sample marks a key first step in allowing us to trace the full life cycles of binaries and will hopefully allow us to constrain the most mysterious phase of stellar evolution." End quote. In general, to study stellar evolution, we're stuck with looking around the sky and hoping we find stars of different ages and otherwise similar characteristics. This is a bit like trying to understand human aging by looking at everyone in an airport on a holiday weekend. Sure, you're unlikely to see the rare 6-day-old and the more rare 106-year-old, but you can get a snapshot of life for at least a sampling of humanity. But if you want to understand the life of one particular star, you're going to be pretty out of luck unless that star happens to be our sun, in which case Earth's geologic and botanical records sometimes let us see indications of things that we are very glad we haven't experienced. I'm just going to read the beginning of a press release from the University of Arizona to you so you can see what I mean. Quote, "The northern lights were visible much farther south than usual this year, and pictures of the colorful hues filled social media. Now imagine an aurora hundreds of times brighter, except no one would be able to snap a photo of it, as the onslaught of particles rushing in from the sun would instantly turn smartphones into bricks." End quote. Only 6 such storms are known to have happened in the past 14,500 years, and the most recent one happened in 664 BCE according to carbon-14 measurements. These solar storms are so powerful that they enhance the amount of carbon-14 formed in the upper atmosphere and later taken in by trees. By looking at tree rings from ancient wood samples, researchers could nail the dates of these events. Unfortunately, they couldn't tell us why they occurred when they did. So while I, for one, am going to continue to wish for more mid-latitude northern lights, I'm going to ask that we don't go setting any records. I like my electronics just the way they are, thank you very much. This work appears in Communications, Earth and Environment with first author Irina Panishakina. After a break, we're going to give you a glimpse of the Dark Energy Spectroscopic Instrument's latest results. We could probably do a whole series on this survey's latest tranche of papers, but I'm going to do what I can with just one segment. Stay tuned. Back in 1998, astronomers learned that contrary to everything we'd ever taught our students, the universe appears to be accelerating in its expansion. Why it would be doing this or what could be causing this was utterly unknown. And for lack of anything better, we named this unknown facet of our universe dark energy. In the 25 some odd years since this discovery, researchers have confirmed through multiple methods that yes, our universe is accelerating in its expansion, and we have started making headway in trying to figure out when it existed and to what degree. What started as a series of imaging surveys conducted from the ground has now evolved to include high-resolution spectroscopy, and spacecraft like the Roman Space Telescope are being built to continue looking for clues. But honestly, after reading the latest stack of results coming from the Dark Energy Spectroscopic Instrument, I'm starting to feel like those future programs will be confirming results rather than searching for something new. And that result, as weird as it sounds, is looking more and more like black holes are the source of dark energy. Seriously. As Einstein would have been among the first to tell you, his theories don't accurately describe what is going on inside the event horizon of a black hole. Where light can't escape, we can't see what is going on. And that is where our knowledge, perhaps until now, had to stop. Einstein's work within that event horizon predicts that mass will collapse down to a singularity, and that isn't something that our understanding of stuff and things can really make sense of. And while relativity and gut instinct are rarely well paired, the idea that something can take up no space is just brain-breaking in not a good way. And it also breaks our basic rule, the cosmological principle, that the universe is basically the same everywhere. If you have a black hole forming a singularity in a volume of space, that volume just can't be averaged out to keep everything the same everywhere. While theorists can't do anything with gut instinct not being okay with relativity, they can look for ways to make black holes play nice with the cosmological principle. In a 2019 paper in the Astrophysical Journal, Kevin Crocker and Joel Viner look specifically at how compact objects play into the expansion of the universe, and they find that these objects, which had previously been ignored, can actually exert an outward pressure on the universe. If I'm reading the paper correctly, they look at the energy supporting compact objects against collapse. Early in the universe, we didn't have compact objects, but as the earlier massive stars died, their extreme internal pressures fundamentally changed what our universe looks like when averaged out. And while my way of looking at this maths makes it sound like this is just some weird fluke of how averages work, the truth is these pressures, called vacuum energy, have a very real effect on the universe. They push it apart. And here is where physics starts to feel like it is creating something from nothing. As their mathematics plays out, a compact object embedded in an expanding universe is getting stretched like a rubber band, and the energy from that stretching is observable as a growing black hole mass. It's that whole E equals mc squared thing. Crocker and Viner made a series of predictions about how the growth of black holes should be coupled to the expansion of the universe, how binary pulsars should be observed to decay, and more. And first in a 2023 paper and now in a new paper, researchers have looked at populations of black holes in the cores of elliptical galaxies where they don't have anything to eat. And they have looked to see if these black holes appear to be growing over time. In the first paper, researchers looked at populations of otherwise similar elliptical galaxies at 1/2, 1/3, and the current age of the universe, and measured the mass of their central supermassive black holes. If all is working as I learned in grad school, those black holes should have the same distribution of masses in all three populations. But if Crocker and Viner are right, they should be coupled with the growth of the universe with a coupling strength of 3. It's just a number, but it's important that it's 3. Using data from the WISE survey, SDSS, and Cosmos, they found a coupling of 3.11, which is really close to 3. And there were error bars, and 3 was included within those error bars. Now, using substantially better data from the first year of data from the Dark Energy Spectroscopic Instrument, a team led by Crocker have looked at how dark energy has evolved over time. I'm just going to read to you from the summary of their paper. Quote, "If dark energy is produced from the conversion of baryonic matter, that's normal matter, into cosmologically coupled black holes, the dark energy density will increase as massive stars form and collapse into black holes, rising from 0 toward a plateau as star formation quenches at Z is less than 2, end quote. What that's saying is they predict that as the largest stars form black holes, we'll see a cosmological constant come into existence. And as star formation stops being maxed out at a particular time in our universe's history, that cosmological constant becomes constant. This explains why we see different Hubble constants from the cosmic microwave background and supernovae. Continuing to read from their paper, they write, quote, "The Hubble rate today is higher than that inferred from the cosmic microwave background because of the conversion of baryons into dark energy during star formation, causing an earlier transition from matter to dark energy dominance," end quote. This is saying that our universe fundamentally changed between the cosmic microwave background and now. Along with explaining dark energy, this also explains how neutrinos have a non-zero mass. Somehow, that one I didn't follow. And it explains why we see a lower baryon density today than previously predicted. All this from just not assuming we could ignore the effects of compact objects on the average density of the universe. We all know what they say about assumptions. Okay, that was just one result from year 1 of data from the Dark Energy Spectroscopic Instrument, or DESI. This is a collaboration of over 900 scientists from more than 70 institutions, and they had 8 new papers come out on November 19th. Central to these papers is one key statement. DESI researchers found that the way galaxies cluster is consistent with our standard model of gravity and the predictions from Einstein's theory of general relativity. There is little to no room in their observations for the extra terms predicted by modified Newtonian dynamics. While potentially sorting dark energy straight out of the gate, they have also made it clear dark matter is largely, if not wholly, made of stuff. Their results also look at the evolution of the large-scale structure of our universe and find nothing unusual. A dark energy and cold, low-velocity dark matter model explains what we're seeing. This analysis focused on year 1 data. At this point, 3 years of data are now in hand, and these results should only improve as more data is included. In January, at the American Astronomical Society meeting, A lot of these results will be discussed. I'm not going to that meeting, but I will be following along remotely and will bring you more news from this project as it is published. Up next, Erik will be joining us for Tales from the Launchpad. Stay tuned. Next up, I'm pleased to welcome on aerospace correspondent Erik Madaus for this week's Tales from the Launchpad.
Hi, Pamela. On November 10th, China's CAS Space launched another Kinetica 1 rocket into orbit from the Jiuquan spaceport. Let's watch the launch. On board 15 small sats for various Chinese companies and the Chinese military, including additional members of the Yunyao, Zhiyan, Yaogan, and Tianyang series. On November 11th, SpaceX launched the KoreaSat 6A satellite from Launch Complex 39A. Let's watch the launch.
5, 4, 3, 2, 1. Engine ignition and liftoff of the Falcon 9 rocket on the KoreaSat 6A mission. Falcon 9 has cleared the tower.
KoreaSat 6A is the replacement of KoreaSat 6, which was launched in 2010 and has reached the end of its service life. KoreaSat 6A will hopefully be in service for 15 years. The Falcon 9 first stage on this mission, Booster 67, launched and landed for the 23rd time, setting a new record for the Falcon 9 fleet. On November 13th, China launched the Haiyang 401 satellite into orbit from the Haiyuan spaceport. Let's watch the launch. Haiyang 401 is the first satellite in the latest generation of ocean salinity monitoring satellites. Haiyang is the Chinese word for ocean, and the satellites provide important data on climate change. On November 15th, China launched the H Tianzhou resupply spacecraft into orbit towards the Tiangong space station. Let's watch the launch. This time, it carried 7.4 metric tons of supplies to the station. The spacecraft docked successfully to the station a few hours after launch. It will remain on the station for a while before being filled with trash and unneeded equipment and deorbited. On November 17th, SpaceX launched a satellite called Optus X for the Australian telecommunications company Optus. Let's watch the launch.
3, 2, 1, ignition, and liftoff. Go Falcon, go TD7. Vehicle is pitching downrange. M1D TR pressures are nominal.
Unusually for a commercial communications satellite launch, SpaceX did not show any camera views of the second stage and payload at the request of the customer, focusing entirely on the first stage landing after staging. This practice is usually reserved for government satellites. On November 18th, SpaceX launched the GSAT-20 satellite from Launch Complex 39A. GSAT-20 is a communications satellite for the Indian government built by ISRO. It was supposed to launch in 2020 on an Indian rocket, the GSLV Mark III, but was moved to an Ariane 5 rocket for a 2019 launch moved back to a GSLV Mark III in 2021, and moved to Falcon 9 in early 2024. There were also 5 launches of Starlink satellites since the last show. The patch I want to feature this week is the one for GSAT 20. I was drawn to it because of the colors, not the usual various shades of blue, some gray, some black, some white of most patches, but orange and green. It's a circle like many patches, but the pattern inside is intricate. It's a SpaceX patch, so it has their characteristic 4-leaf clover, but it just shows the satellite, not the Falcon 9 rocket. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the United States has had 124 launches, China has had 56 launches, New Zealand has had 11 launches, Kazakhstan and Russia each have had 7 launches, Japan has had 6 launches, India and Iran each have had 3 launches, French Guiana has had 2 launches, and North Korea has had 1 launch. This makes the total number of launches so far this year 220. Finally, there are 9 toilets in space. Of these 220 launches, there have been 4 failures, reminding us that space is hard.
Thanks, Erik. Before we go, I just want to bring you a bit of good news from a girl named Emily. I initially heard about this story from a friend named Emily, who let me know another Emily in her Emily's Only Facebook group had been offered a trip to space. The Emily she was excitedly telling me about was Emily Caladrelli, the SpaceGal, a science influencer who has long made it known she dreams of going to space. With a Master's of Science in Aeronautics and Astronautics from MIT, Emily worked really hard to make her dreams a reality, all while encouraging others to learn and explore our world and space with her through her writing, video shows, and television. And on November 22nd, Emily became the 100th woman to travel to space as she flew above the Karmen line on a Blue Origin New Shepard. Here's to hoping her continued efforts allow her a longer visit someday in the future, where she can use her education to do some research. And that's it for now. Good night, everyone, and remember to go out and look up. Oh, and please give this video a like and subscribe so the algorithm tells you and the world when new science is ready to be learned.